Well, greetings, mathletes, and welcome back. Today we're going to be talking about function composition. Now, there's actually five operations we're going to be looking at altogether. The first four, well, they're more just about understanding what the notation means because we don't really use them much for computation. They usually show up in proofs or in explanations of why things work. So those first four, it's just a quick explanation of what these things mean when you see them. The fifth operation is function composition, and that's the one that we're going to spend the most time on. So I'm going to start out by just kind of giving you a quick rundown on what all the different notations mean, and then we're going to spend the rest of the lecture working on function composition, because that's the one that, if it's new to you at all, it takes a little bit of thinking to get through, although it's not overly complicated once you understand what's going on. So let's go ahead and get started here. Okay, so the first four operations. Let's make sure my pen's on. There we go. Ooh, let's thin that out a little bit. Okay, so the first four operations we're looking for are function addition, subtraction, multiplication, and division, right? And we've actually done all of these things before. You've done them in previous classes, but you may or may not have seen the notation for this. So if I have f plus g, right, that's two functions f and g added together. What that means is you just take the function f of x and add it to the function g of x. If I have f minus g of x, that's taking the function f of x and subtracting g of x from it. If I have f times g of x, that means take the function f of x and multiply it by the function g of x. And the last one is function division, which means take f of x and divide by g of x, right? As long as g of x isn't 0, right? So as long as g of x is not equal to 0, you're good there. Okay, so those are the first four. Now this is going to make a lot more sense if I if I go ahead and define some functions. So let's pick a couple of functions here. So let's say f of x is equal to 2x plus 3, and g of x is equal to x squared plus 1. Okay, so those are my two functions. Those are the two functions I'm going to be dealing with here. Okay, so let's just look at these one at a time real quick. F plus g of x literally means take f of x, 2x plus 3. It's a good idea to remember the parentheses, and add g of x, which is x squared plus 1. Right? So you add them together, you collect your like terms, you actually end up... now, keep in mind, sometimes it's better to not add them together because you actually need them separate. But, from here, you would just collect like terms. F minus g of x would be the exact same thing, but with a subtraction between them. Right? So you literally just add or subtract the functions together. F times g, and you probably already have it figured just from looking at the first two, even if you haven't seen this before. But that's 2x plus 3 times x squared plus 1. Right? You're going to FOIL that out if you need to. You may not need to. Sometimes it's better to leave things factored like this. And then the last one, f divided by g, would be 2x plus 3 divided by x squared plus 1. Now, like I said, these things really show up more in theoretical context. You very seldom see this written over and over and over again. If anything, they would just define the new function to be the sum of the old functions or the product of the old functions or something like that. But it's just a way of writing it down without having to write out the entire function every single time. So these are primarily just for theoretical reasons. Now, the fifth operation, and actually, I think, well, let me do this. Yeah, we're going to be focusing primarily on this fifth operation. I want to leave those functions there. So we're going to keep the functions the same for the moment. F and G are still going to be the same. And we are going to look at function composition. And what's good about this is function composition begins with fun. I know the argument could be made that it also begins with FU, but this is a family show, so we're going to keep it starting with fun. In any case, this is the definition and symbols that you use to define function composition. So if I'm composing two functions, I use an open circle between them. It looks much like the multiplication, but it's an open circle. So I would write f composed with g of x. And the way we compute that is to take f, and we're going to tuck g down inside of it, right? So whatever the x is for the function f, we're replacing that x with the function g. So a couple of things here. So one, and by the way, this x value, I'm completely just picking it random. I'm picking it because it's a nice number and it's easy to compute with. Let's suppose we wanted to find something like f composed with g of 2, right? And again, you can pick any number you want. I'm picking 2 because it's nice to compute with. So let's look at what that means. The definition here says we're going to be looking at f of g of x. Oh, excuse me, not x, 2. Right? So we're sticking 2 into g, and then we're going to take that number and stick it into f. So if you look at this, and if you want to try to start from the outside, you have a problem here because you can't compute f until you know what g of 2 is. So we can step to the side and look at g of 2. Let's see, g of 2 would be 2 squared plus 1. So that gives me a 5. So g of 2 is equal to 5. So what we do from there is we make the substitution. Now we want to see what f of 5 is, right? Because g of 2 is equal to 5. We found that. So f of 5, well, let's see. What does f do? It multiplies its argument by 2 and then adds 3 to it. So this would be 2 times 5 plus 3. So that gives me 10 plus 3, which is 13. So f composed with g of 2 ends up being 13. And you notice when we did that, we actually had to start on the inside with g of 2, figure out what that number was, and then plug that number into f. Okay, so sometimes this function composition is said, instead of saying f composed with g of 2, sometimes it's said f after g of 2. And if you think about it, that's the order you compute it in. You compute f after you compute g of 2, right? So I actually like that that terminology to say f after g. It's not very common. In fact, most of the people I hear using that terminology are learned their mathematics in other languages and then translated it to English. But I really like that notation. Now, let's kind of map out what's actually happening here. So if I have, in fact, let me switch the color on this. I'm going to go back to the old traditional thinking of functions as just a machine, right? So this one is g, and this one is f, right? So let's look at what we did. What we did was we took 2 and we shoved it into g. Oh, I should probably give it an output place. Right, there's a hole where everything comes out. So we stuck 2 into g, and g spit out, well, it spit out this 5 over here, right? And then we took the 5 and we shoved that into f, and f spit out 13. So really what we're doing is we're taking a number and we're feeding it through one function at a time, taking the output from one function and making it the input for the other function. And again, you notice, if we're doing this, f composed with g of 2 ends up being 13. So you end up running it through both of these. Now, here's where the problem comes in, is that you have two functions. If you're going to be sitting here plugging values into two functions over and over and over again, it actually gets a little bit old after a while. It would be much nicer to just have one single function to deal with. And that's actually what we're going to be focusing on. How do you find an expression that gives you one function that you can compute the composition with? So let's take a look at that. I'm going to get some of this off of here. So we already know that f composed with g of 2 is 13, right? And we just worked all this out. So here's how the composition goes if you don't have a number, right? If I want to compute f composed with g of x, it's f of g of x. And as I mentioned before, g is acting like your x value now, right? That's your input. So let's look at what f does. F takes its input, multiplies it by 2, and then adds 3 to it. So you notice I just took the x would normally go right here, and I just took that out. I just pulled the x directly out. What I'm going to put in its place is g of x. Right? So I took x out, I put g of x in its place. Okay, well, if we stop and think about it, what is g of x? G of x is x squared plus 1. So now I'm just going to put an x squared plus 1 here. And from there, I can go ahead and distribute this 2 and collect any like terms I have. So that's going to turn this, let's see here. That's going to be 2x squared. And then 2 times 1 is 2. And I'm going to end up adding it to that 3. So it's 2x squared plus 5. So this should be our composition. So let's see. So if we're claiming that f composed with g of x is 2x squared plus 5, then when I plug 2 in here, I should get a 13 back out, right? Because they should give me the same value. So let's see what happens. If I stick a 2 in here, that is 2 times 2 squared plus 5. 2 squared is 4, times 2 is 8, plus 5 is 13. And so I get my 13 back, right? Now, we're going to be going through a few of these things. So I know this was kind of a little bit chaotic. We're going to be taking a look at more direct examples here, ones that we're not going to worry so much about plugging in individual values. That's the purpose that we're learning to do this. But what we're really going to be needing to do is what's right here. We need to be able to find the composition function, right? And so that's what we're going to take a look at. So let's go ahead and clear all this off and take a look at a couple more functions. All right, so let's say f of x is equal to 3x minus 4 and g of x is equal to 2x minus 7. And I'm going to be looking for two things, right? And I'm going to be looking for the composition both directions. So that means that I'm going to be looking for f composed with g of x, and I'm also going to be looking for g composed with f. Now I'm doing both of these to show you that you can't just switch the order that you're doing this in. This is, once you see a direction of composition, you can't switch that order. It has to be the direction, it has to be the direction specified in the notation, because if you do it the other way, most probably you will get the wrong answer. So let's look at these one at a time. We have our functions here. Let's start with f composed with g. Okay, well, we know f composed with g is f of g of x. And what I like to do is I like to just start with the outside function, right, and write down the function rule, but I don't put the x in. I'm just going to leave parentheses because everywhere there's an x, I'm going to stick the other function. So it's minus 4, and since what I'm putting into f is g of x, that means g of x goes here. Okay, well, we know what g of x is. So I can take this, the 2x minus 7, and put it in for g of x, right? And now from here, I just need to simplify my expression. So that's going to be 6x minus 21 minus 4, and that leaves me with 6x minus 25, right? And so my composition is this expression, right? That's the composition function. So again, just to kind of look at what we did, I started by writing the definition. That's the definition of composition. And then I just looked at what it meant. I started with writing down the rule for f, but with a blank spot so that I could insert whatever the input was. The input was g of x, and so I put it in place of x. Then I took the rule for g of x and I plugged it in for the name of the function, since these two things are equal. These two guys, g of x and 2x minus 7, are the same value. So I just substituted them. And then once I had that, all I have to do is simplify, right? That's the idea. And so this is our composition. You get a completely new function, and yeah, that's pretty much it. Okay, so that's our second example. So now I want to go ahead and look at the other direction, right? G composed with f of x. Well, that means g of f of x, right? That's our definition, that it has to be equal to that. Well, let's see, what's the rule for g? G takes its argument, multiplies it by 2, and then subtracts 7 from it. So my argument is f of x, so I'm going to put f of x in here. From there, I can just look at what the rule of f of x is. So I know I still have this. The difference is f of x is 3x minus 4. So now we'll go ahead and distribute this. So that gives me 6x minus 8 minus 7, which gives me 6x minus 15. And so you notice they're not the same function. They have the same slope in this case, right? They're both linear functions, but they have completely different y-intercepts, which means they're not the same line, which means they can't be the same function, right? So if you compose in the other direction, you get a different answer. There are cases where you get the same answer, and we will see some of those. But you typically will get a different answer unless you get lucky, right? Okay, so that's our first example. So let's go ahead and clear that off and take a look at the next one. Okay, so the next example, let's do g of x is equal to x squared plus 2x, and h of x is equal to 2x plus 1. Okay, so we have a square in here that we want to deal with. And what we're going to be looking for, we're going to find g composed with h, and then we're going to find h composed with g, because we're going whole hog. Okay, now let's go ahead and take a look at g composed with h. Okay, so if you have g composed with h of x, we know that that is g of h of x. G takes its input, squares it, and then adds it to twice its input, right? So it does all of that, right? And notice I put parentheses every place that there's an x. Well, the input here is h of x, right? So next step would be to just plug in the algebraic expression that represents h of x, which is 2x plus 1. So now this is 2x plus 1 squared plus 2 times 2x plus 1. Okay, so you would be expected to simplify this, although I will say a lot of the time when you find a composition in the course of solving some other problem, sometimes it's easier if you don't simplify it until you have to, because, you know, there's just things you can see in here sometimes. Okay, so let's go ahead and simplify this. If I go ahead and square this out, that's going to give me 4x squared plus 4x plus 1, and then distributing this gives me plus 4x plus 2, and I would just collect my like terms to get, let's see here, 4x squared plus 8x plus 3, right? Okay, so that's the first one. So that wasn't too bad, but we did have to do a little bit of other algebra to figure out what the simplification looked like. Okay, now let's look at h composed with g, right? So we'll look at it the other direction. And we know h composed with g is h of g. And let's see what h does. H takes its argument, multiplies it by 2, and then adds 1. And we are dropping g into it. So that means that our expression is now 2 times the algebraic expression for g, which is x squared plus 2x plus 1. So if I go ahead and distribute here, that gives me 2x squared plus 4, plus 4x plus 1. Right? And so that's h composed with g. You notice it doesn't look anything like this other one. They don't match up at all. Other than the fact that they both happen to be squaring functions of some sort. Yeah, they're actually quite messy. So keep that in mind. You have to do it in the right order or you get two different answers. So make sure you read the question carefully and look at what it's asking. All right, so that's our second example. So let's take a look at another one here. So let's get rid of that. And let's see here. Okay, so let's suppose we have, let's see. Let's say h of x is equal to the square root of 2x plus 1, and r of x is equal to, what do I have here? X squared plus 4. Okay, so these are two new ones, right? We've seen squares before, but we haven't seen square roots. So let's check this out. Let's see what happens when we look at h composed with r of x and r composed with h of x. Okay, so what I want you to do is go ahead and pause it here and see if you can work out these compositions on your own, and then when you're ready, or whether you be, in a position where you're stuck or you've already solved it, just go ahead and push play and let's see if we match up. Okay, so go ahead and pause it here. Okay, I'm assuming you've paused it. And so let's walk through these one at a time. So let's look at h composed with r of x first. So again, it's h of r of x. H takes the square root of twice its input increased by 1, and its input is r of x. Okay, so now we just need to plug in the the expression for that. So let's take the square root, and that's 2 times x squared plus 4 plus 1, which is, let's see here, let's go ahead and distribute that. So that's going to be the square root of 2x squared, and then that'll be an 8, and then plus 1 makes it 9, plus 9, and I'm taking the square root of that, and since that's not a perfect square, it doesn't factor. It's not even like a nice factor pattern or anything. So that's as far as I can go. That's my function, right? I didn't have to do anything with the root in this particular case. All right, so hopefully you matched up with that. Let's take a look at the other one. Let's look at r composed with h of x. Now remember again, that's r of h of x. So let's look at what r does. R squares its input and then adds 4 to it. Right? So let's see what happens there. So that means we're putting h of x in here. And so we're going to be squaring h of x. We just need to substitute h of x for its expression. So that h of x is the square root of 2x plus 1. And let's see here. Well, if I square a square root, they cancel out. So this is now 2x plus 1 plus 4. So it's 2x plus 5. Right? Notice these are very, very different answers. So again, the compositions, you do not get the same expression if you do that in opposite directions, at least for the most part. So, pay attention to that. I'm sorry, I keep having to fight myself. Normally my first reflex is to go, okay, so are there any questions? That's not going to work here. So, questions, you can approach me in office hours and we'll go from there, or email or what have you. And let's try the next one here. Okay. Let's see here. How about f of x is equal to 1 over x squared plus 2x, and g of x is equal to x plus 2. So again, just like the last time, let's see if you can find the composition in both directions. So f composed with g and g composed with f. So go ahead and pause it here and see what you can find. Okay, so I'm assuming you've paused it. The questions here usually have to do with how much simplification is actually required. That is entirely going to depend on what you're using it for. Sometimes you end up needing to have a single fraction for things. Sometimes you don't need a single fraction for things. So things are going to, they'll be different. But let's take a look here. So we'll start with f composed with g. So we know that's f of g of x, just like before. So again, let's look at what f does. F, let's see, we have 1 over, let's see, its input squared plus its input doubled. Okay, and the input is going to be g of x. Notice I'm putting it everywhere I see an x. And I think I'm going to run out of room before I get to the second example. We'll just use it up. Okay, so from here now, this is 1 over, well, we're going to substitute in the formula, which makes it x plus 2 squared plus 2 times x plus 2. Right, so we have to do a little bit of algebra here. We're going to have to square that guy out if we're going to simplify this. So this is now 1 over x squared plus 4x plus 4. And then we'll distribute this one out. So that's plus 2x plus 4. And if we go ahead and collect our like terms, I get 1 over, let's see here, x squared, it's going to be 6x, and 4 plus 4 is 8. Yeah, right? And so there's our simplification. Sometimes you need to factor it, sometimes you don't. If it actually turns out you're adding that term to another fraction, you're going to have to factor the denominator. But unless you're in a situation where you have to, there's no point in doing it. Okay, so that's the first composition, F composed with G. Now we need to head back the other direction. Okay, so just to make sure we saw, this is our final answer here for that first one. Now we need to look at the second one. Now the second one actually goes pretty quick. So I'm just going to do this. These are funny. They're very deceptive sometimes. Sometimes they go very fast. Sometimes they require eye-bleeding algebra. So it's just a matter of which card you get handed. Okay, so G composed with F. That means we're sticking F inside of G. You know, one of the ways I always think about this, especially later on, is I always think about it as like layers of an onion. When you're trying to look at the composition, you're peeling off layers of that onion, is what you're really doing. Okay, so let's see here. G takes its input and adds 2 to it. Well, in this case, the input is F, so we'll put F in here. And F is this fraction, x squared plus 2x, and it's plus 2. Now, in many cases, this is perfectly fine. There's nothing wrong with this answer in and of the way it's written, right? This is very commonly given as an answer. Sometimes, though, you are required to find a common denominator and make it a single fraction, okay? So if you have to do that, what you do is, well, this has a denominator of 1, so that means the common denominator is x squared plus 2x, right? So I'm going to multiply the top and bottom here. In fact, let me get this out of the way. To get a common denominator, I'm going to multiply by x squared plus 2x on the top and the bottom. And that gives me this first fraction plus, well, I can just distribute this now. 2x squared plus 4x over x squared plus 2x. Now they have a common denominator, so all I have to do is add that 1 to it. And that gives me, let's see if I can have enough room here, 2x squared plus 4x. Actually, let me switch colors so it stands out. So it's there. 2x squared, right? That's this term. Plus 4x, right? That's this term. And then plus 1 over x squared plus 2x, right? And so that's another form of the answer. Again, though, this is fine. I don't suggest doing extra work unless you have to, because every step you take when you're working on a problem is one more place you can make a mistake. So if you can do it in fewer steps, there's fewer places to make mistakes. So, and if you're like me, I make arithmetic mistakes quite often. So I try to minimize the arithmetic as much as possible because, well, it's just less places for me to screw up, to be completely honest. Okay, so let's look at another example. There we go. Now, so let's take a look at f of x, oh yeah, is equal to, oh, let's make it 2x minus 3, and g of x is equal to x plus 3 over 2. Okay, and I want you to find f composed with g and g composed with, that's actually right what I'm saying here, g composed with f of x. Okay, so find both of those. Go ahead and pause it here. Okay, so I'm assuming you've paused. So if we're looking at F composed with G, we know we're doing this again. F composed with G of X. F takes its input, multiplies it by 2, and then subtracts 3 from it. The input is G of X. Right? And we know the expression for G of X, so we can plug that in now. So this is now 2 times X plus 3 over 2 minus 3. Well, conveniently, the 2's cancel, and that gives me X plus 3 minus 3, and the 3's cancel, and that gives me X. And that is the full composition, right? When you take F composed with G of these two functions, you just get X back. Now what that means is whatever you put into this, whatever number you put in there is the number you get out. So if you put in a 1, you get out a 1. If you put in a 2, you get out a 2. If you put in negative 5,476,000, you get out negative 5,476,000. Right? So whatever you put in comes back out if the function is just equal to X. Now, if we look at this the other way, G composed with F, right? Well, that's G on the outside, F on the inside. And let's see here. So G is our first one. So I'm going to take my input, add 3 to it, and then divide that answer by 2. Well, my input is F. So let's see here. Let's see what we get. F, I know what the expression is. So it's, oh, that didn't switch colors. Come on. Forgive my fingers. So F is 2x minus 3. And in this case, the parentheses aren't actually needed, so we can just collect our like terms. Negative 3 plus 3 is 0. So that means that this is the same as 2x over 2. And then, again, the 2's cancel. And I'm left with just x again. Right? Now, these types of equations, the relationship between these two functions is actually a pretty important one. They're what we call inverses of each other. So if you compose two functions both directions and you get x back each time you do it, then those two functions are inverses of each other. Now that's a little bit of foreshadowing, right? Because we will be talking about those later, but they do come up quite often in terms of function composition. You can actually tell with some of these things. Like if I go back up here and look at these, let's see here. Let me make some space. Probably should have been a little more efficient about that, but okay. Right, if 2x minus 3 is one side of an equation, right, and that just equals something. Okay, if I were to solve this, let's think about the steps you would take to get x by itself, right? I would add 3, and then I would divide by 2. Well, what does g do? When you have an input, it adds 3 to the input and then divides it by 2, right? And so that function actually is all of the steps it takes to solve that particular equation. If I look at it the other way, if I have x plus 3 over 2, and I think about what I need to do to solve something that, I'll just say it's equal to a number, I would multiply by 2 to get rid of the denominator, and then I would subtract 3 from it. And that's exactly what this function does. It multiplies it by 2 and then subtracts 3. So these functions undo each other. All of the operations in one are reversed in the other one. And so that's what makes two functions inverses of each other. And that's going to come up again later, and that's pretty important, actually. But I did want to mention it. I wanted you to see what it looks like before we actually get to this and when, it matters and stuff. because they will pop up in the homework, but no attention is drawn to them. It's just they're there, just so you can kind of get used to them. Okay, so that's the last of finding the composition. I want to take a quick look at what happens in finding the individual functions that can make a composition. So we'll have a few examples of this. And this actually becomes very important in calculus because if you can identify certain things as a composition, it makes the math a lot easier. So if I'm given a composition of functions, let's say h composed with f of x is equal to the square root of x squared plus 6, right? What we want to do is we want to find a function h and a function f so that when I compose them this way, this is what I get, right? So we're trying to figure out what was composed to get here. Now, there's certainly more than one way to do this, but these are done in a way that one function is the obvious inside function. And in this case, I think it's probably fairly clear x squared plus 6 is the inside function, right? Well, this f is the inside function, so that means we have x squared plus 6 here. Oh, that didn't switch. There. Squared. Okay, now we have to ask, if this is an x squared plus 6, how do I get that square root on it? Well, I have to be plugging that x squared plus 6 into a square root function for that to happen. And so that makes the other function the square root of x. So now if I look at this, h composed with f of x, right? H is the outside function. I'm saying it's the square root of x. So let's see, it's the square root of whatever my input is. And that's f of x. And f of x is x squared plus 6. So this is x squared plus 6, and that matches. And so we win. Now, these don't really necessarily require any computation. If you can just see it, which is the goal, right? The goal is for you to be able to look at it and just be able to see a composition. If you can see it, all you have to do is write them down. Write down the two functions. If you can't see it, though, you might have to do a little bit of work. Maybe figure out one function and then try to find an inside to that, or you might have to mess around with it a little bit, and then go back and build the composition to see if you got what you think you're supposed to get. Right? So let's look at a couple more functions here. So let's say our composition, let's say g composed with f of x is equal to the absolute value of 4x plus 4x minus 7, right? Before I answer it, pause it for a second, see if you can jot down an answer. Okay, so pause it here. Okay, so I'm assuming you've paused it. Now, looking at this, what we can do, I'm going to look at this one a little bit differently. I can see this absolute value here, and it's on the outside. It would be the last thing that I would compute if this was an order of operations problem. So that means g of x can be the absolute value of x. Well, now I need to find a way to get this expression inside this absolute value. Well, that means that f of x should be 4x minus 7. And then you can go and check the composition, g composed with f, the way we were doing it before, and make sure it actually lines up the way you think. So let's see, g is an absolute value of whatever the argument is, which is f of x. And f of x, we're saying, is that. So this should be 4x minus 7. And if you can come to the same answer that you started with, you win, right? It totally works. So we did find two functions that give us this composition. Okay, I want to look at one more example of this, and that'll pretty much be it at this point. Okay, so again, same thing. Let's look at f of x, f composed with g of x is equal to 1 over 3x cubed minus 7x. Okay, so pause it here and see if you can jot down the functions. Okay, so I'm assuming that you've paused it here. Now, this one looks a little bit different because of the fact that I have this fraction thing here. Well, if I go ahead and look at 3x cubed minus 7x, that's a pretty good expression there. So let's go ahead and call that one of our functions. The worst thing that can happen is this doesn't work. So let's say g of x is 3x cubed minus 7x, right? So we want to ask ourselves, right, what would f of x have to be so that when I shove this in, I get this fraction? And it has to be something that puts its argument in a denominator, right? So whatever the input is to this function, it has to go in the denominator. Well, that means that it would just be 1 over x, right? Because that means the input goes into the denominator. So let's take a look at this. So let's say we have f composed with g of x, and we're using these two functions. So we're just going to see if these work. So let's see here. F takes its input, and it actually just takes the reciprocal of its input. And in this case, the input would be g of x. And let's see here. G of x is this guy. So that means this is 1 over 3x cubed minus 7x. And it matches, right? So we get exactly what we wanted here. This guy sometimes causes fits, just so you're aware of it. It really can cause some issues just because it's new. We haven't dealt with it as much. But it's just a matter of it. You just need a function that tells you where to put the other function so that it matches up. That's really all it is. And again, I really want you guys to be able to look at these and just see what the composition is, because that's the skill you really want to take with you into calculus, right? There's a particular rule that makes a lot of computation a lot easier, and it's called the chain rule, and it has directly to do with function composition. So, in any case, that wraps up pretty much everything I wanted to cover today. So we've looked at function composition. We've looked at a whole bunch of different examples of this thing. And remember, what it is really just taking one function and shoving the other one inside of it and seeing what you get out of it, which function comes out. So in any case, until next time, keep your pencils and your wits sharp.